Great. Thanks everyone for coming on this Wednesday morning. I'm XY. I'm an assistant professor of operations management at the University of Chicago and also a member of the Applied Artificial Intelligence Center there. And this talk will be on this line of work I've had since, I guess, 2017 on neural collapse in deep net training. And the main content of this work will be from these two papers. One is from this PNAS paper we published in 2020. We published it in 2020, but the work started even in 2017, called Prevalence of Neural Collapse During the Terminal Phase of Deep Net Training. And then this follow-up we had in 2022 in ICLR, which won the Outstanding Paper Award that year. My co-authors on this are Vernon Papillon from the Applied, who's an assistant professor in the Applied Math Department at the University of Toronto, and Dave Donahoe, who's a professor of statistics at Stanford. And for the SDSC folks, this is Dan's dad. And this is the obligatory slide that every AI person likes to put at the start of their talk. So I'm gonna try to get through this fast, but it kind of sets the tone of things. Which is in 2012, we kind of all know the story, which is AlexNet broke all records on the Fei-Fei Li's ImageNet competition. Like it did, what, 10 percentage points better than the thing that was the best classifier in the previous years before they were stuck around 20-30%. Suddenly, AlexNet came in and just did a complete reset of the field with a 10% improvement. And since then, the performance has just been getting better and better. Again, this thing truncates at 2019. Nowadays, we know that we have vision transformers, we have multimodal models. So this is probably down to something that's imperceptible at this point. And again, on this axis of the size of these models, they've been growing larger and larger. This is a plot from 2018 on what was the best models back then. And the largest bubble you see back then was this 150 million parameter models. But nowadays we have these like 70 billion parameter models for, say, Llama or something. And the performance has just been going up. And if we were to adjust this chart and extend it out to what we can do nowadays, it's even bigger. And we'll probably go off the slide. So the point of just taking a snapshot at the beginning of things is that it shows this paradigm shift that happened in 2012 that we're all kind of still adapting to, which is this rapid growth of models and the rapid growth of the variety of models out there. Like each colored bubble here is a different architecture. And part of this new paradigm shift is this idea that performance matters above all. It's not like you have to follow a certain recipe to do well anymore. You don't have to, say, use the Fourier transform. You don't have to use a particular kernel. There's just one thing that decides whether you're remembered by the community or not, and it's your performance on contests or your performance on benchmarks, and in general, it's your competition score. And for researchers, this creates a rather frustrating situation because you check arXiv now, and every morning, if you're lucky, there's maybe 200 new papers on arXiv. If you're unlucky, like before a conference or something, there's probably a few thousand. And every one of these new papers will propose a new architecture. They'll come from a different team of researchers somewhere in the world. And they don't share any sort of common reasoning or foundation system from which they were derived. It's just that this particular team at this particular time came up with this particular intuition and idea, and they built an architecture based on this idea, and it just happened to work for them, and that's what they published. So it becomes a problem and a source of frustration for theorists and academics in general, because there's now a lot of particularities to each one of these publications, and it saying something about any one of them might not generalize in a broad sense of that word to the other models that will be published even in the same day. And it seems implausible, especially during the 2012 to 2016 window, that we might again find some sort of regularity across all these data sets and architectures that are out there. So yes, that's the general emotion. And the point of this talk is to talk about this behavior that we found called neural collapse around that time, that despite all that chaos with architecture and data sets, neural collapse is a common outcome of deep net training that leads to a precise geometric structure emerging from that training process. And by analyzing and thinking about this geometric structure, we can actually gain some useful theoretical insights as well. But then we should occasionally step back. And I get this question sometimes, which is, what's the point, right? Like, we've already mentioned that it seems like we're in a community centered on performance. So what is the point of stepping back and thinking about these deep nets as if they're high dimensional vectors and analyzing that? The way to think about this is the performance metrics we see on these benchmarks tell you about the score that these deep nets achieve, that each architecture achieves in whatever contest or game that they're playing. While if we look at the geometry, we can start getting a sense of what is the strategy that these deep nets are learning, because we're training them using the same thing, really. We're training them using some gradient method, whether it's SGD or LoRa or AtomW, right? Like, we are not training them to follow any sort of rules or any sort of mechanics. But if we look at the geometry, we can actually start piecing together what they're actually doing under the hood to perform so well. So that's what this geometric point of view gives us. And so now we're going to set this up. So the most abstract way to think about deep classification nets, at least in this context, is using this diagram right here, which is you have an image that we'll call XIC for the rest of this talk, and you put it into a deep net. That's this blue box right here. And most deep nets, even LLMs nowadays, are partitioned into these two components. One is all the layers prior to the last one, and we typically call that the feature engineering step. And by the end, there's convolutions, there's skip connections. Nowadays, there's attention layers, and vision transformers have like tokenizers that converts patches to attention to tokens, which then goes through the attention layers. But in the end, they output this thing that's called a feature. And for our purposes, we'll be focusing on the feature that happens right before the last layer linear classifiers. And what these classifiers do is these are vectors that multiply these features, and whichever multiplication, so there's one for each class you want to classify here, and whichever one gives you the highest number, that's what you're predicting as the final class of your input data. So this is the diagram for image classification nets. And this schematic actually did not change that much since it was created. For example, even LLMs effectively follow a similar schematics. Instead of an image here, you just have the context of the sentence, for example, that you're trying to encode. You can think of this either as the raw sentence, in which case you would have to put the token encoder inside the feature engineering, or you could just think about these as the encoded tokens. But in the end, you push it through the feature engineering that in an LLM would be some attention layers. And in the end, again, by the end of most LLMs, you'll again have this classifier, and the classes now correspond to the predicted token that that particular attention layer wants to predict. So for the class, this talk is going to focus on image classification, but this schematic is a lot more general than that. And what's to remember here is just the input's going to be called X. The feature that's learned in high dimensional space is going to be called H. The linear classifiers that hits those features will be called W. And the scores will just be calculated with a W times H vector inner product, which for the people who haven't taken linear algebra in a while, it's basically you have like a vector is a like stack of numbers, right? And so like a 2 vector is what is like 1, 2, 0.5, 0.3. A 3 vector is 0.3, 0.5, 0.7 or something. And an inner product is you take, say you have 2 of these number stacks, you multiply them element-wise. So the first number times the first number in the second stack, the second number in the first stack times the second number in the second stack, the third number times the third number in the third stack. Now you have 3 numbers and you add them together. That's called an inner product. And to some degree, it tells you how similar these stacks of numbers are to each other. And what neural collapse reveals is that during training, these feature vectors, H, and these classifiers, W, across multiple data sets and multiple architectures, they actually converge to the same geometric structure. How are these stacks of numbers geometric? Well, you can think about these stacks of numbers that I mentioned as coordinates in high dimensional space. Like in high school, we all learned about the XY axis, right? There's 2 numbers, and the first number tells you where you are horizontally. The second one tells you where you are vertically. In high dimensional space, it's just each number in the stack gives you a coordinate in the corresponding dimension of space that you're in. So when you think about these things as high dimensional vector coordinates, then they start becoming geometric objects. And we're going to be tracking these geometric objects, and we're going to be tracking them in this particular regime, which is typically now there is some literature on, say, early stopping, which is when you should stop your training. But usually what people do when they do have enough data is that they just preset a number. For medium-sized data sets, that's usually like 100 to 300 epochs. For huge data sets, usually that's like 50 to 100 epochs. And you just try to train until you memorize the training data. And so that's what I mean here by zero classification error. And you train until the loss, which is the cross entropy loss has the quotient of different exponential terms in it. This loss can actually not ever become 0 exactly for mathematical reasons, but you're trying to push this loss to 0. And this happens much later than when you effectively memorize the entire training set, because memorizing the training set just means your network makes the right prediction. But your network makes this prediction based on the numbers that it outputs at this stage. And these numbers could always get better by the fact that like the biggest number could just get bigger compared to the rest. So you're training past memorization, effective memorization, and towards really driving the actual training loss to a zero asymptote. Right. Okay. So here's the equation. So this is just the number of training images you classify, and this is actually the training loss. And because of these exponentials, you can actually never get this to exactly zero, but you can keep getting it closer. And here's the diagram where you can see what corresponds to what. And the reason we can do this at all is because these networks are massively over-parameterized. They give us the flexibility to do this memorization and this push towards zero. With the classic methods before 2012, we definitely couldn't have done this. And now we're making measurements. What are we measuring? The first thing we're measuring is these classifiers. Again, considering them as vectors or points in high dimensional space where each number gives you a coordinate in a particular dimension. And they'll be represented by these red ball and sticks in this diagram. So each class that we're possibly predicting corresponds to one particular vector classifier. The other thing we'll be measuring are these features that are transforms of this image after it goes through the preliminary layers of the deep neural net. They'll be represented by these small balls here. So each one of these spheres corresponds to a different image, either in a training or the test set. And finally, we'll be measuring the mean of those image representations for each particular class. So for example, if we take all the cars, we have a cloud of balls in high dimensional space. We'll just take their average location, and that's what we'll call the mean of that particular class. And they're represented by these blue ball and sticks here. So now what quantities, as we're starting to do science, we need to start quantifying different ideas. And the first idea we want to start quantifying is the idea that in high dimensional space, if we view these image features as spheres of high dimensional space, each one of these point clouds has a spread, has an internal spread within the class of cars or the class of cars, or the class of cats, for example. And to quantify this, we take the difference between each individual point in high dimensional space and their center. And this is actually called the within class covariance in statistics. And then we take because this is a high dimensional object, we take what's called an outer product, and this creates a matrix. For mathematical reasons, this gives you a lot of information about the skewness and the tiltedness of the point cloud itself, but we don't really have to think about that now. But the most important thing is notice how this matrix is defined. It's defined by taking the difference of each one of these little spheres with their average location, which makes sense because you're trying to capture the spread of each of these point clouds. And the other thing we want to capture numerically is, we talked about the individual point clouds, but we also want to talk about how the point clouds themselves are spread apart. And to do this, we just look at the centers of those point clouds. So there's a global center that we'll call mu g, which is just the center of this diagram. And we'll be taking the difference between each of those class means with the global mean and calculating, again, this inner product, which for math reasons gives you a lot of useful information about this geometry. So that's what is called the between class covariance. We'll be analyzing that. And knowing that, we can actually, this is where we're going. This is the goalpost, which is all of the quantities I showed in the previous diagram converge to, with training, to what's called a simplex equiangular type frame, which are high dimensional vectors in their whatever dimensional space they're in. You're going to spread out these vectors to be as far from each other as allowable, and they're going to end up being the same length. So in three-dimensional space, it'll just look like this Mercedes-Benz shape here. And this diagram captures everything I'm going to be talking about during this talk, which is you start really random, but as you train, the means will converge to this shape. The classifiers converge to this shape. The little image representations all converge to its mean. So basically, each one of these point clouds collapses to its mean. And actually, the blue and red sticks converge to each other, which is the classifier for each class ends up just being the same vector as the mean of that particular class. So now I'm going to start formalizing those words that I just spewed out. So the first thing we found about neural collapse is that, again, each one of the features, so we can each one of the feature clouds ends up just collapsing to their corresponding class mean. And the way we measure this is this is the trace operator, which effectively just measures how big this matrix is in terms of the numbers inside it. And what you see is that the size of each one of these point clouds as measured by this quantity becomes small compared to the size of the separation between the cloud centers themselves, which is what we divide by here. And as we train, we see that this number just shoots downwards towards 0. And what it shows is that, again, each one of these tiny spheres is going to its class mean. The second thing I mentioned is that the blue and ball and stick is approaching the red ball and stick, which means that, oh, wait, this is not there yet. So the other thing is this simplex equiangular type frame, which is, notice how everything's becoming very symmetric by the end of training here, right? They're forming this tetrahedral Mercedes-Benz looking shape. And the way we can capture that is we can actually use linear algebra tricks to calculate the angles in high dimensions between any two of these vectors. And for any two, so the idea is we can see how much variation there is between the angles between any two pairs of vectors, and they become the same. And this is what this quantity is measuring. You don't actually have to think too hard about this. Just trust that the math works. And also they're becoming the same length. Again, we could just do this using linear algebra, just measure the length of that vector in high dimensional space. So all it's saying is it's becoming symmetric and all of them are converging to the same length. That's NC2. And finally, the blue ball and stick is converging to the red ball and stick, which means that, again, the W's are used to classify each particular example. The mu's are just the centers of each one of these point clouds. And what's interesting is that basically they're becoming the same thing, because when you calculate the score, which is you're multiplying the mu by the W, you're taking the biggest one, which says which W is most similar to your particular example. And to do a correct classification, you want the W to be almost exactly the same as your example, at least the W for the correct class. And so the neural net is really learning this geometry, this internal representation correctly. So that's the third property. And again, notice that we're doing this across different networks. So VGG, ResNet, and DensNet, which were the three networks that were available on PyTorch at the time. This was 2017, 2018-ish, and then 7 data sets, which starts simple from MNIST and goes up to CFAR 100, then up to ImageNet. So these are the properties. And what does this give us? So the idea is if the classifier vectors are just approaching the class means of the training data, what you end up actually doing when you make a classification is you're actually just finding for each new example HIC, which doesn't have to be a training data example now, you're taking the representation of that example and you're comparing it because the WCs are the same length and also the same as the class means. You're just finding the closest cloud center within the training data. And you're saying, oh, let me compare my new example to the existing point cloud centers and just assign my new example the cloud center that it's closest to. This should actually be C prime. So this is, we don't know what this example is, and what we actually want to do is we want to find the class of this example rather than have the class already with it. So there's a typo here. And we show that, and empirically we show that on test data, so not data that we trained, we showed that effectively the network's decision ends up becoming the same decision as just taking the training data's class centers and doing this comparison. So here it is laid out in mathematical notation. So the first property is that the within class covariance goes to 0. The second property is that the angles become the same and also the lengths of the vectors become the same. The third property is that the blue ball and sticks converge to the red ball and sticks, which just means the classifiers converge to the class means. And under the first 3, you can actually just show as a consequence, but also it's nice to state by itself, which is when you classify a new example, which is this calligraphic H here, you actually end up just doing the nearest class center rule, which is comparing it to all the class centers in the training data. And this does seem to have some benefit, which is it correlates with an improvement in generalization performance. And the way we can see this correlation is so this is something that happens beyond memorization. So here, each of these red lines is basically where the DeepNet effectively memorized the training data. And you can see, like, with the small data sets, like, it becomes so small that you can't actually see anymore. But with something bigger like ImageNet, you can actually see that this neural collapse behavior actually goes down more even after you effectively memorize the training data. And so as you train beyond memorization towards just pushing the loss down, you get closer and closer to this tetrahedral shape. And this convergence to the equiangular height frame actually does lead on the out of sample test data to an improvement in performance, even though sometimes it's small. It's not completely true. There are a few of these where it gets worse, but for most of them, it gets better. So there is a correlation there between the formation of this structure and the improvement of the DeepNet in out of sample generalization. And there's also a correlation between this and the adversarial robustness of the network, in the sense that as you train beyond memorization, which happens at this red line here, your network actually becomes more robust to adversarial noise as measured by the deep. So we call this axis robustness, but this is actually the deep floor metric, which is how much noise you need to add to the network before the deep floor algorithm works to trick your deep net into classifying an image into something else. And the way you can think about why is this geometry useful is that there's a slogan that we like to say, which is neural collapse ends up being the preferred end state of every successful exercise in feature engineering. For example, if you look back into, say, the 1960s with Claude Shannon and information theory, it turns out that what's a optimal code book in Shannon's coding theory ends up just being a simplex equiangular type frame if you get to design the code book yourself. And we have a theorem about this in our paper. And if you look at the 1990s, there are people, in particular Webb and Lowe, who just derived mathematically what should be the optimal linear classifier for any given set of fixed features. And it turns out that if your features are an equiangular type frame, then the self-duality property we saw in our experiments should actually hold, which is the optimal classifier for a equiangular type frame is the self-dual equiangular type frame. So it relates to classic regression theory from the 1990s as well. And from more recently, there was this line of work that said that deep nets are just doing max margin classification under the hood. And in fact, if you allow the data points to also move, which is the case in feature engineering, then the best configuration for the max margin classifier is the equiangular type frame. Because as these margins push apart, you want to push all the examples to one single point, and you want to push them in a way that they're maximally separated from each other. And we have a theorem about this in our paper as well. So that's the idea, which is that's what neural collapse is. And through this, we can start connecting it to these ideas that we've had in the past about what feature learning is and what those feature classifiers should look like. To finish off, that's what we did. And then later on, there were quite a few works after this. So the question was, okay, this happens on training data. Does this happen on test data? And the answer, and also on other layers of the network. And the answer was provided by Tomer Galanti in these two works. He showed that like the test neural collapse is you can't see the numbers here, but it effectively mirrors the training data in the test data, but there's around a 1 order of magnitude difference between the train and test data, but they look, the degree of collapse look roughly the same. And also, if you go through the layers, as you go deeper into the network, you get this gradual increase in the degree of collapse. Now that we know this property, we can start using it to start building better deep nets. Like some people have proposed just fixing the last layer into an equiangular type frame and seeing how that goes. It does speed up training a little bit, but it kind of actually corresponds to just replacing the data one-hots with ETF vectors, but that's a different thread. And then also, we examined this behavior in data sets where the relative classes are fairly balanced and equally represented. When you don't have that equal representation in the training data, it does actually lead to imbalances in the equiangular type frame. In particular, different means and classifiers actually end up collapsing to each other. For example, if you just had one example of a dog and one example of a cat, for no reason other than the fact that they they're underrepresented in the data set, they'll actually end up being pushed into the same class mean vector, because everything's trying to push each other away, and the two underrepresented class will be collapsed onto each other. And this is a behavior called minority collapse. So by looking at it through this geometry, and by knowing that the ETF is sort of the reference structure that we're looking for, we can actually identify deviations from this structure and also build new architectures from this structure. And recently, this work by Verdon and his research assistant Robert, as well as, again, Tomer Galanti, Randy Ballestiero, Andrea Pinto, showed that you can see, again, the LLMs effectively followed the same input data, tokenization, feature engineering, classifier schematic that I showed at the beginning. So now that LLMs are a thing, these groups showed that like the same neural collapse and also the skewedness property when you have a data imbalance happens in LLMs. So that I think I'm definitely over time, but the idea is we're in a regime that puts a lot of emphasis on the score, but if we look at the geometry that happens within a deep neural network, we can start understanding the strategy that the deep net takes to actually make its decisions. Neural collapse is one of those perspectives that we could use. And it's a behavior that happens across different canonical deep nets and data sets. It's characterized by these three properties here. And I'm very happy that after we published the paper, there's been a lot of follow-ups on it, and it's been able to generate some new ideas in the community. This is just something I've been recently thinking about, which is this collapse behavior actually happens without labeled data. So you can see in self-supervised learning, which I'm doing with Marco and Jack, as you train a feature learning classifier without the actual class labels, you'll see that images from the same class actually, again, end up collapsing to each other. And there's ways to validate, like this is what people usually do, which is the score, right? How these SSL methods perform. But you can, again, measure the geometry using these between class and within class matrices to look at them. And again, this geometry gives you a pretty good indication about how the actual score will be. So that's it. Sorry for going over time, but thank you for listening, and that's the talk.
Wonderful. Thank you so much. I saw, Khan, you had a question, I think probably about halfway through. I don't know if you want to ask that question, but we've got a few minutes that we can spend asking any questions on this work or anything more generally.
I think you're muted.
Yeah, or your mute is off, but I can't hear you.
All right, you guys should be able to hear me now.
There we go.
Yeah.
Yeah.
Yeah, I was just following up on Ahmed's comment. We had the tag open during the presentation, so we couldn't see the lower part. But yeah, all good now.
Cool. Jack.
Thanks, XY. That's really interesting. I had two questions, so I'm going to be greedy. So the first one is, do you see a future for like deep nets that is more in line with like reinforcement learning or sequential decision problems, whereby you're learning a policy based on this the way you're trying to make the two axes converge, rather than shooting for an accuracy score, so that you can then like have people, like you said in the beginning of the talk, have people aim for different kinds of policies to achieve the same kind of outcomes? And then my second question was, when looking at the axis and how they converge in training, what is the mechanism as it relates to that when you start overfitting? And you see like losses go back up, does that like then the convergence kind of shifts and pushes them away again, or does it stay there but like there's something that makes the generalization across like vowel sets and stuff worse? So those are my two questions.
So that's a great point that I think also is very relevant right now because of this whole DeepSeek disruption from a few weeks ago. So the thing about reinforcement learning and policy learning is that we're actually doing two different things. One is we're trying to translate these rewards that we observe from the environment into a target that is more deterministic, and the other, which in RL is represented by this underlying value function, which then you can derive a policy from. And then the actual there's this feature learning part that's actually trying to predict either the Q function or the value function. And now we're working with two different components. What is unclear at the moment, and what DeepSeek kind of forces us to think about, is what role does the rewards to value component play? Should that, like, in what way should that be done? And that's like the feature learning part can be thought of, in my view, as just this collapse to whatever desired state space you want that sufficiently separates the data in a correct way, because in the end, you're making a prediction. The RL part, it's still up in the air. And the RL part is also up in the air because it works in a different regime. The RL part usually works unless you're, say, one of the alpha 0 or something in the small data regime. And overfitting generally happens in that regime. This is why you see people train for 300 epochs on big image data sets, but you have to stop at the 5th epoch if you're training a RL classifier, because then you'll start overfitting because your data, you just don't have the data to do that type of fitting. Otherwise, your rollouts will take forever. So the second part of that RL problem is, ironically, a small data problem. So, and what I think has not been sufficiently disentangled from the narrative, because we keep thinking about this as a pipeline, as we should, because it is a pipeline. But the pipeline perspective actually hides the fact that you're dealing with a two-component process. The first component is the supervised fine-tuning process is a big data problem. And the RL component of that process, in which you can overfit, is actually to some degree a small data problem. And how we integrate this is still up in the air. And DeepSeek just pushed it to a more visible level. Yeah, so the answer is I don't know, but this is how I think we should be thinking about it.
And so you're up next.
Right, thank you. Thank you very much for your presentation. It was really interesting, and it was great to have like just an overview of classifier for just like, I think it was like really satisfying, I think. So thank you very much. I have one question. So for the neural collapse, and you talked in terms of the classifier, right? So I think in terms of classifier, I think it would definitely work. because it is collapsing into one single point, right?
Mhm.
But when you're dealing with, let's say for the re-identification model, or something that you still have to push same class into a certain point, but still have to have some differences between each of embeddings or the spaces, how do you foresee this plays along?
Yes. So this gets us into self-supervised and unsupervised learning territories, like what you guys are doing with the surgical data recognition, and you have to pre-train because, like, I think so far we have 16 videos. No, we have 3,000 videos, right? But unlabeled. So and you have to be able to distinguish these different features, but you don't have the data to actually add labels to them. And this has been like the torture of my life for the past 2 years, is the thing I've been working on is how does this work when you don't have class labels. And people, like, again, in deep learning, the annoying thing is, or the good thing is, the empirics generally lead the empirics generally lead the actual theory and the actual understanding. So in self-supervised learning, even in, say, the Sinclair paper and the Dino papers, we start to see this collapse of different like what we humans know are semantically related data points to each other. And we don't know why. We just know that for some reason, if they take these features and plug it into these visualizers, they collapse, and they can actually get linear probe accuracy out of it. So it does happen. But why does it happen? And this has been one of my research points the past few years that we stop sharing, that I've been looking into. And the idea is, when you train any sort of self-supervised method, you're trying to collapse images of the augmentations of the same image to each other. And that, to some degree, will kind of induce a local collapse of the features. And the annoying thing is, because you don't have labels, any two distinct images, whether they're augmentations of each other or not, must push each other apart. And this push and pull process creates it forces a collapse. A collapse must happen somewhere, but the regularization on this prevents it from completely just going to zero. And this is so far the understanding. Quantifying this is really difficult. It's taken me 2 years and I still haven't been able to do it. But in the end, that's the intuition. And it's hard to say precisely, but I think whether it's me or someone else out there, it is something that we have to eventually characterize. If we're like academia, at least, has to characterize to gain an understanding of how feature learning works. But I think you're hitting on exactly the right point.
Okay, thank you very much. I think that kind of gave me overall picture of where the collapse and where that can be a little bit expanded, so that there's each of point that is unique, so that you can distinguish it. I think that gave me a little bit of idea of it. So thank you very much.
Thank you for the question.
Thank you. Okay, I think we've got time for possibly one more question if anyone is keen to ask. But if not,
I think one more.
Oh, Khan, here we go.
Yeah. So yeah, thanks again for the presentation. I just want to understand this phenomena from the data point of view. Like, could you correlate, you know, what kind of data is more likely to lean towards this kind of collapse in terms of, in terms of its size, in terms of its of the balance of the data, because a lot of times you will have to deal with unbalanced data sets that kind of tips you to one direction more than the other one. I see neural collapse is actually essentially might be a good thing to for infer in some cases maybe, but it might also be disadvantageous if we are to lean towards one side of the equation here, like one side of the classes, let's say, especially if you have an unbalanced data set, and or if you have a data set that's not big enough, obviously, which you kind of touched on with the supervised with the pre-trained models of training all these data and all that will be useful in that case. But just want to give you have an opinion from you on how data matters in terms of experience the neural collapse.
Yes, that's a great point. And people have been thinking about similar things. For example, the minority collapse phenomenon I mentioned is that if you have two, regardless of what the classes are, if they're too represented in the data, all the underrepresented classes in the data will end up being pushed to the same feature representation, which is bad. Generally speaking, the difficulty in inducing collapse generally corresponds to how hard it is to extract signal from the training data. For example, ImageNet doesn't MNIST collapses after 10 epochs. ImageNet doesn't collapse even after 100 epochs. This made our ImageNet experiments much more expensive.
Mm-hmm.
And the idea is we have to reshape these. So the feature learning process is reshaping in a somewhat consistent way the raw pixel data or the raw token embedding data, whatever data type you're using, into a high dimensional vector, which is again a stack of numbers that can then be separated using some linear regression ways to your ends and decision-making needs. And the key word here is we have to do this in a consistent manner. And by consistent manner, I mean a definable architecture that is the same applied to every data point that you input into it. And it takes a more complicated architecture and longer training because you need to tune the parameters more. The more mixed up and convolved together your input data is. And at some point, if your input data is so mixed together that you're actually unable to extract the signal from it in any sort of reasonable way, even a deep net will fail. And for a long time, this is why LLMs didn't work.
Right.
Because language, it was very hard to encode through traditional MLPs, the relational structure between different parts of a sentence. And you can't just pass the entire document to it because then the MLP will become huge to the point even modern GPUs can't handle. And this is kind of why transformers actually worked, and LSTMs kind of sort of worked because they reduced that learning process into something structured. They're whether it's with key query relations or with a running state memory. So the answer is the data definitely matters, because if the data becomes too difficult for your architecture to unmix, then you need a bigger architecture, or you need a more complicated architecture, or you need a different architecture. And the balance also matters because when you train this architecture, it's not going to know that it needs to be fair. And if you give it more things to in a particular subset of the population, then it's going to learn that subset to the detriment of the underrepresented data points in that population.
Yeah. Thanks. Yep. I thought this.
Thanks for the question.
Yeah. Thanks for the explanation. Yep. Makes sense.
All right. Well, folks, we're at 2 minutes past the hour. So we've taken up plenty of your time, Dr. Han. From all of us, thank you for joining us though. Really enjoyed this
Thank
talk.
you for the invite.
And folks, have a great day wherever you are in the world. Speak soon.
Great. Thank you very much, everyone, for coming. Bye.
Thank you.